Hello. So it's kind of late, but I did want to do a little bit more work on the permutations program, and we'll see how far we get today. The stuff I want to add to it is generating or finding orbits of points. I am not at all prepared to talk about the group theory involved here. I'll try to explain the theorems I'm using, but I'm not going to prove anything or anything. I'll save that kind of thing for a later video. Okay, so let's say that we have the Rubik's Cube, okay? I'll just do a crappy drawing. Hey, you know what? Oh, I just had a great idea. Yeah, I wonder. Oh, yeah. Okay, we have a cube. How do you get rid of this? Oh, no, I don't want that. Go away. Oh, there we go. Show canvas. Okay. And done. Done. How come I can't rotate anymore? Oh, 3D view. Okay. All right, so pretend this is a Rubik's Cube. What we could do is label each position on the cube, okay? So I'm labeling positions, not stickers. We could call this position 1, position 2. I'm only going to do a few of these, by the way. Position 3, 4, 5, 6, 7, 8, 9. And then maybe we continue on this side with 10, 11, 12. Okay, I think that's enough to get the point. A clockwise rotation of the top face would have the effect of moving the sticker at 1 to the position at 10. It's nice how the arrow sort of goes on the cube like that. Okay. Likewise, a counterclockwise rotation would take the sticker at position 12 and move it to position 3. But here I'm talking about the positions. Kind of like if I rotated the cube, the numbers would sort of stay at the same spot, but the cube would rotate past them. Okay. Now, the orbit of a point, very simply, is all the points that can be reached from it. So it's kind of obvious, but a corner point can go to any other corner point. Actually, I take it back. I'm not sure if it's that obvious. But obviously, by turning this front face clockwise and counterclockwise, we could move the sticker at position 1 to any of positions 3, 9, 7, back to 1. If we rotated this left face counterclockwise, let's track the position of the sticker, so we'll use a little orange dot. A little orange dot for that. If we move the left face counterclockwise, the orange dot would move here. Again, the numbers don't move. Then with clockwise and counterclockwise rotations of the top face, I could move it to any of these points, and then I could shift it down here and get any of these, and I think you get the idea. But at no point could the sticker, which started at position 1, under any combination of moves, ever end up at position 2. Right? That can't happen. Okay, so what I want to do today is a methodical method of discovering the orbit of a point under the generators of a permutation group. If you don't know what any of those words mean, it's okay, but I don't know how much the rest of this is going to make sense. Okay, well, let's get started. Last time, we sort of discovered that our representation of permutations, where we have all of the positions and arranged in this vector with, it's hard to explain this in words, as in we have the cycle notation for representing permutations stored inside of a vector events, basically, right? We're thinking of it in terms of cycle notation like that, okay? But we discovered that gap actually does the easier to manage notation, internal notation of a table. It's an array. The value of the array at index I tells you where the element at position I travels under this permutation. So open up all my advanced, teaching tools over here. The tabular representation, I don't know, I'm making this up here, 6, 4, 5, 2, 3, 1. What that tells us is the item which started, actually we can draw this. Oh, now I want regular paint for this. Okay, we have 6 objects. We start out with 6 of them. Maybe I'll make them different colors. This is very likely to be explaining something which is incredibly obvious to anybody who's even bothered to click on this video. So I really don't know if this is worth the trouble, but anyway, this is just to make sure that we're all on the same page. Mostly for me, actually, because as you might have noticed in previous videos, I misunderstood some very basic things. We figured them out eventually, but we lost time on it, so maybe doing this ahead of time would be worth the trouble. Okay, so what this tells us is if the item started in position 1, it'll end up in position 6. And if this item started in position 2, it'll end up in position 4. Come on. So we can draw that like this. So the item in position 1 ended up at position 6. The item in position 2 ended up at position 4. The item at position 3 ended up at position 5. The item at position 4 ends up in position 2. Ooh, which color was that? Yeah. The item at position 5 ends up at position 3. And the item at position 6 ends up in position 1. Alright, so nothing too earth-shattering here. Alright, so gap uses this representation. It doesn't need this vector up here. This is just the index, the labels of the indices of the vector. Okay, the gap would store its permutations like this, and I can kind of see why. It makes the algorithms cleaner. It's more efficient in a lot of ways. The only time it's less efficient is if your permutation only deals with a few elements out of the whole set, and that's not really going to be the case very often. So I am vaguely tempted to change the internal representation to this. But we don't have to do that right now, because what we can do is we can write code which will be agnostic to whichever representation we're using. That's what we'll do. Okay, so I do want to explain the end goal in a little bit more detail. Yes, I want to generate the orbit of the point, but I don't just want to list all the positions that the number 1 could end up in, right? 1, 3, 7, 9, 10, 12, etc. I would also like to list which combination of cube moves moved it there. So 3 is part of the orbit, but I also want to keep track of the fact that turning the front face clockwise is what brought 1 to that point. Okay. So in the end, we're going to have something like a tree where we'll start with the point whose orbit we wish to consider, and we're going to sort of have like a tree which says if you turn the cube forward, you go from 7 to 1. For reasons which are not at all obvious, I actually want my tree to have the arrows pointing back to the orbit, whose orbit we're considering. The reason for that is not going to make sense until, you know, a later video. So actually what we're going to do to build this tree is we're actually going to scout around using the inverses of the permutations. So I would start at 1 and check F inverse. That takes me to 7, and then I would write it like this in the tree. Of course, I could have written it like this, as in with just this arrow instead of just that arrow. Both are equivalent, but I'm going to notate it this way. Okay, and we'll do like, I don't know, you sort of get the idea. I don't really want to get into it too much, but if we do F inverse from 1, we get 3, and if we do up, the up face, well actually if we do up inverse, we get from 10 to 1. Okay, so we're basically going to do a breadth first search and fill out this breadth first search tree of the orbit of 1. Okay, that's our end goal. This data structure is going to be really helpful when we move on to some of the algorithms we're going to use later. Okay, now this could be difficult, but I'm hoping it won't be. So I guess let's get going. The final representation of this data structure is actually going to be an array. Each element of the array is going to be the permutation we would apply that takes it, I guess, up the tree back to the root. Okay, so here, how do we get from 1 to 1? Well, we apply the identity. How do we get from 2 to 1? I haven't discovered this yet. That would get filled in later. How do we get from 3 to 1? We apply F inverse. How do we get from 4 to 1? I haven't filled it in yet, but well, actually, I don't think we can. Yeah, 4 is on the edge here. So actually, at the end, these would be null, or some, you know, suitable empty type. How do we get from 5 to 1? We can't. And so on. You kind of get the idea. From 7 to 1, we apply F. And the permutation that we have in here doesn't have to be just one turn of the face. Like, for example, after we get to 3, a U inverse would take us from 12 to 3. So 12 might be discovered in the breadth first search tree like this. And it would be represented in this vector as U inverse. Well, shouldn't we have U inverse F inverse? Well, we could, and I see no reason against that, but for now this is sufficient, because then what we'll do to find out the entire generator, I'm using the word generator absolutely incorrectly. It's just, the proper word is coset representative, because of what we're doing with this. But even if you were a mathematician, you wouldn't understand why I'm talking about coset representatives. I'd have to set up the whole thing, and I don't have what it takes to do that today. Anyway, to find this, I guess, chain of moves, which takes a dot at position 12 and moves it to position 1, we apply U inverse, and we see where that takes us. Well, if we apply U inverse, that dot moves to position 3, and then we would look up in the vector again. Oh, now we apply F inverse, and then we get to 1. F inverse, right? So U inverse, and then F inverse. Okay. So for now, we're going to build the orbits tree like this. And this is actually known as a Schreier vector, or Schreier tree. It's probably better to call it a tree, but originally Schreier described it as this vector, so they're called Schreier vectors. Okay, so this is our end goal. Then in that case, it's going to be, no, actually I should do it like this. I should make it a free function. I should start moving these into separate files. I can do that later. It's going to return as a vector of permutations. Orbit int position, and we're going to have a set of perms, which is going to be the generators. Generators being the allowed permutations that we're using on the edges of this tree and their inverses. So I need to have set, I guess I could make that a vector actually, it may be better. It's just easier to think of generators as a set, but a vector would be better, so I'm going to do that. We are going to need sets though, so I may as well leave that. Now, we need to implement a breadth first search. Okay. So we need a queue. Is that right that we need a queue? Yes. So Normally when you do a breadth first search, you keep a queue of nodes. We also need to keep track of which nodes were visited, but it just so happens in our case that the nodes that we visit is the orbit. So we would probably like to return that too, wouldn't we? It is implicit in this object because if a point is not part of the orbit, it'll have a null in it or something at that location. So maybe we don't have to, but we have to keep track of it anyway. I'm thinking. Okay, well, let's see what we have for a default constructor. We don't have one. We should have one. So this is going to make a empty permutation. And we should just make it the default. And let's have an operator bool to tell whether or not this is a real permutation. So here we'll just return. If names is default constructed, it will be empty. Okay, that seems all right. So here, we're assuming that all of the permutations in the generators are drawn from the same namespace. Okay. Boy, I would really like to have an identity permutation though. An identity permutation is an identity permutation will be in a namespace, but data will be empty and cycles will be 0. Yeah. Okay, perfect. In that case, I would like perm from just a shared pointer to an nmap to just set names to n and cycles to 0. Ooh, will that compile? Oh, yes, surprisingly. Yeah, so if you just give it a shared pointer, it'll make an identity permutation. Okay. Now, here I will do well, I was tempted to do this. Gens 0 arrow names dot n and perm of gens 0 arrow names. You know what? I think I'd like to do shared pointer to an nmap namespace is equal to gens 0 arrow names, and here I can just use names. Whoops. Okay. Okay, and at the end, that's the vector we're going to return. So it starts out as, oh wait, that's not what I want. That's what I want. Yeah. I don't want an identity permutation yet. Yeah. Okay, so I'd like to have a queue of int, which is, I'm going to call it frontier, and it's going to start at, it's going to have just pause in it. Okay. Now we're going to do while queue. I actually have never used a queue in STL before, so I need to check the. Hold on a minute. I need to check the API. I actually don't know if you can initialize a queue that way. Let's just see if it compiles. Ooh. Yeah. Yeah, okay, you can't initialize it that way. But we can do something kind of cheesy, which is like that. Initialize with one copy of pause in it. Now I'd like to know how to check if it's empty. Yeah. Actually, I wonder if it has. No. Yeah, while not my queue.empty. That's what I want. Queue.empty. Frontier, not queue. Alright. What we are going to do now is int cur is equal to frontier dot pop maybe. Front. Pop. I want to remove it. Yeah. Oh. I actually need to do frontier.front and then do frontier.pop. Yeah. I did know at one point why you have to do this, but I'd have to think about it to remember. It has to do with destructors. And if you try to return it but then destruct it, it gets messy, something like that. Okay. And now we want to do for each of the generators. So we should like to invert it. We would like to invert it. Messy. It's messy. So basically, I would like to have some operator to apply the inverse of a permutation to an int. So I guess I'll use a different operator for that. I almost want to use the unary minus operator. And in fact, gaps permutations have an extra bool in there. All right, let's do that. So for all of these, we'll start inverted as false. Oh, wait a minute, what am I doing? This is the delegated constructor. Yeah, I don't want to be doing that. Yeah, like that. So we should check if it's inverted in the multiplication operator. Ooh, what does multiplying by the inverse do? I really would like to have it. This always happens to me. I always forget some thing along the way. Okay, I may be a little too tired for this. I knew it was a bad idea to start this late. let's think about it. If I have 1, 2, 3, 4 times 3, 4, 5, 6 inverse. How does that change the multiplication? Oh, it changes everything. Because now scanning backwards is exactly the wrong direction. We want to scan forwards in the inverted permutations, and we still want to scan right to left, but we may scan forward through the cycles instead of backwards. Now that is gnarly. Is there a nice way to do that? I think we can do it. Okay, I'm gonna put that as a to-do because it's not high on my priorities at the moment. No, I really should do it now. All right, fine, we'll do it now. So we still want to go through these cycles backwards, so this much is right. I'm starting to realize just how few comments I put in here. Oh, just watch the video. You don't have to have comments if you have it recorded. Yeah. Stupid me. Other dot cycles at I minus 1 is rightmost element in this cycle. Temp is the value of that element. Location of the right parenthesis C the art of computer programming. I should be able to do this, but it's late. Yeah. So here what we would do so cur is going to start out as 1, 2, 3, 4, 5, 6, but here we're actually going to travel forwards, so we're going to leave the left parenthesis here. We'll swap the 3 with the 4, yeah, the 5 with the 4, the 6 with the 5, and then the whole with the 6. Yeah. Okay. Okay. We can do this. I can do this. I think it would be better to just simply wrap this whole for loop if other dot inverted is false, then we do this. Otherwise, we do pretty much the same thing, but we move forward instead of backwards within the cycle. So here we want other dot cycles of I minus 1, right? Dot cycle leftmost element in this cycle. Temp is the current value at that position. That's what I should say here. Position, cache the position. For this time of the left parenthesis. Okay, we have done it. Well, not quite. We still have to change this to go in the right direction, but other than that, we're okay. Let me just make sure this makes sense. Also, this should come first. That's a little bit cleaner. And it's all about understanding. Okay. And then just assume the current value at that position. Now, we don't do anything to J. J is strictly less than other dot cycles at I, J plus plus. And cross your fingers. I hope to God that's right, because, well, it's probably fine. It is probably fine. Yeah, sure it is. Okay. And then if inverted is false, then we do this. Otherwise, we do the exact same thing. We take out all the others. Ooh, I hope this is right. I hope this is right. We should really test it. First, let's see if it compiles. Oh, it's stuff in here. Hint reference, give me a break. Fine. Is it push? Oh yeah, push. Okay. Now, let's have a parent reference. Invert. Here we'll do inverted equals not this, and then return star this. Not sure if I really like that, but whatever. We can also do perm operator. This is unary minus, and then perm ret equals perm ret from star this ret dot inverted equals not inverted. So this one makes a copy, this one doesn't. I'm not sure if this is a good coding practice, but it's enough for us to test it. So, okay. It's P2. Yeah, I don't want this dummy perm. Go away. Don't want that. And here I'm going to do P2. I'm going to do times minus P2. Okay, it compiles, and we'll check this all with gap, of course. Shit. This prints out a bunch of stuff that I don't remember what it means anymore. Okay. I hope that's right. I hope that's right. One, 3, 8, 6, 2, 5, 7, 4 times 3, 8, 5, 1, 8, 6, 3. Oh no. Oh, fascinating. Oh yeah. This is correct, actually. It's just not represented in what you might call, canonical form. But this cycle is the same as this cycle. Yeah, reading backwards, or forwards rather, has broken the property that it always leaves it in sorted order after the fact. That doesn't make sense. I'm not sure why it would do that. But I am glad it works. And just for the hell of it here, we can also do P3 equals P3 times minus P3. And that should give back the identity permutation. We'll see what happens with the identity permutation. Uh-oh. We shouldn't see out we should just simply return I. If it's not in the permutation, it doesn't move. Yeah. Now the fact that it doesn't print anything is kind of minor, but we'll fix that. Hey, wait a minute. The identity permutation should have, oh, less than -1. Ah, we don't have to do this anymore because we have changed it to always have the last number in the cycle representation. So hopefully this doesn't cause a seg fault. I'm pretty sure it's okay. Oh man, it's not okay. Okay, well. Yeah. Yeah, that's right. Of course it's not okay. That's easy enough to fix. If p.cycles.size is strictly equal to 1, then return O is the anti-permutation. There. Kind of cheesy, but should work. Yeah. Perfect. I think that table is coming out of the multiplication function, so let's get rid of that. It's bothering me. Okay. Oh, it's in the constructor. Well, I don't want it, so let's get rid of it. Okay, I think we're in business. We just need to edit this operator for when the permutation is inverted with sort of the same idea as we go the other direction if it's inverted. No, I think it's counterproductive to keep working on it. I think I gotta quit. It's taken a lot of effort to focus, so yeah. I'm gonna stick to doing these videos on the weekends. Doing them during the week doesn't really work for me. I spend all day fighting with stuff at school, and it's not as fun to do this during the week. Okay, well, if you have listened, let me know if this is helpful to you at all. Alright, bye.